Electrons and conductors do not flow solely on the outside of the conductor. They move throughout the entire cross-sectional area of the conductor. This is known as uniform current density. Electrons move from atom to atom within the conductor lattice regardless of the physical shape or orientation of the conductor. This is because electrons are not confined to a specific path but are free to move randomly throughout the material. Twisted wire does not necessarily move more electrons than solid wire. The cross-sectional area of a conductor is the primary factor that determines the number of electrons that can flow through it. While twisting a wire may slightly increase its surface area, this effect is negligible compared to the overall cross-sectional area of the conductor. Therefore, twisted wire and solid wire of the same cross-sectional area will have approximately the same electron flow capacity. It is possible that any statement, how it was made in the context of a specific application or experiment. However, as a general rule, electron flow is not significantly affected by the shape or orientation of the conductor. In summary, electrons flow throughout the cross-sectional area of conductors, regardless of their shape or orientation. Twisted wire does not offer a significant advantage in electron flow capacity compared to solid wire of the same cross-sectional area. The amount of current a conductor can carry is primarily determined by its cross-sectional area and its material properties such as conductivity. A larger cross-sectional area provides more space for electrons to flow, reducing resistance and allowing for higher current flow. Different materials have different conductivities, which affect how easily electrons can move through them. Copper and aluminum are commonly used in electrical wiring due to their high conductivity. The shape of the conductor, whether it is solid or stranded, has a minimal impact on the amount of current it can carry, as long as the cross-sectional area remains the same. Stranded wire is often used in applications where flexibility is required, as it is more resistant to breaking when bent or twisted. However, for a given cross-sectional area, solid and stranded wire will have similar current carrying capacities. When selecting a conductor for a specific application, it is important to consider factors such as the required current carrying capacity, the operating voltage, the ambient temperature, and the installation environment. The National Electrical Code, also known as NEC, provides guidelines for selecting the appropriate conductor size and type for various applications. NEC Table 310.15b16 specifies the allowable ampacities of insulated conductors rated up to 2000 volts, based on their size, insulation type, and ambient temperature. It is important to consult the NEC and other relevant standards to ensure that conductors are installed safely and in accordance with local regulations. In addition to cross-sectional area and material properties, other factors can affect the current carrying capacity of a conductor, such as the presence of insulation, the method of insulation, and the grouping of conductors. Insulated conductors can carry more current than bare conductors because the insulation helps to dissipate heat. The method of installation can also affect the heat dissipation of a conductor. Conductors installed in free air can dissipate heat more effectively than conductors installed in conduit or cable trays. When multiple conductors are grouped together, the heat generated by each conductor can raise the temperature of the surrounding conductors, reducing their current carrying capacity. The NEC provides adjustment factors for reducing the allowable ampacity of conductors in these situations. It is also important to consider the operating voltage when selecting a conductor. Higher voltage applications require conductors with thicker insulation to prevent electrical breakdown. The NEC specifies the minimum insulation voltage rating for various applications. In addition to the NEC, other standards and guidelines may apply to the selection and installation of conductors, depending on the specific application and location. These standards may be issued by organizations such as the Institute of Electrical and Electronics Engineers, also known as IEE, the American National Standards Institute, also known as ANSI, and Underwriters Laboratories, also known as UL. It is important to consult all relevant standards and regulations to ensure that conductors are installed safely and in accordance with best practices. The concept of skin effect can influence the current distribution within a conductor at high frequencies. At higher frequencies, the current tends to flow more along the surface of the conductor rather than distributing evenly throughout its cross-sectional area. This phenomenon is known as the skin effect. The skin depth is the distance from the surface of the conductor at which the current density has decreased to 1 divided by E, or approximately 37% of its value at the surface. The skin depth decreases as the frequency increases. The skin effect is more pronounced in conductors with larger diameters and at higher frequencies. In power distribution systems operating at 60 Hz, the skin effect is generally negligible. However, in high-frequency applications such as radio frequency circuits, the skin effect can significantly affect the performance of conductors. To minimize the skin effect in high-frequency applications, conductors are often made of thin strips or tubes, or they may be plated with a highly conductive material such as silver. Litz wire, which consists of multiple strands of individually insulated wires twisted together, is also used to reduce the skin effect in high-frequency applications. The individual strands are insulated to prevent current from flowing between them, forcing the current to distribute more evenly throughout the conductor. In summary, the skin effect is a phenomenon that causes current to flow more along the surface of a conductor at high frequencies. The skin effect can be minimized by using thin conductors, plating conductors with a highly conductive material, or using Litz wire. While the skin effect is generally negligible in power distribution systems operating at 60 Hz, it can be significant in high-frequency applications. The term electron flow is a conventional way of describing the movement of electric charge in a circuit. However, it is important to understand that electrons do not actually flow in a straight line from one point to another. Instead, they move randomly within the conductor, colliding with atoms and other electrons. The net movement of electrons in a particular direction is what constitutes electric current. The speed at which electrons move through a conductor is called the drift velocity. The drift velocity is typically very slow, on the order of millimeters per second. However, the electric field that drives the electrons through the conductor travels much faster, close to the speed of light. This explains why electrical circuits can respond so quickly to changes in voltage or current. The amount of current that flows through a conductor is determined by the voltage applied across it and the resistance of the conductor. This relationship is described by Ohm's law, which states that voltage equals current times resistance, or voltage equals amps times ohms. The resistance of a conductor depends on its material properties, its length, and its cross-sectional area. Longer conductors have higher resistance, and conductors with smaller cross-sectional areas have higher resistance. The resistivity of a material is a measure of its resistance to the flow of electric current. Materials with high resistivity, such as insulators, have very high resistance, while materials with low resistivity, such as conductors, have very low resistance. Semiconductors have resistivity values that are intermediate between those of conductors and insulators. Semiconductors are used in electronic devices such as transistors and diodes. The conductivity of a material is the reciprocal of its resistivity. Materials with high conductivity are good conductors of electricity, while materials with low conductivity are poor conductors of electricity. The conductivity of a material can be affected by factors such as temperature, impurities, and the presence of an electric field. In some materials, the conductivity can be significantly enhanced by the application of an electric field. This phenomenon is known as field effect conductivity. Field effect conductivity is used in field effect transistors, which are widely used in electronic circuits. In addition to electrons, other charge carriers can contribute to electric current. In some materials, positive ions can move and contribute to the current. This type of conduction is called ionic conduction. Ionic conduction is important in batteries and fuel cells. In plasmas, both electrons and ions can contribute to the current. Plasmas are ionized gases that are used in a variety of applications such as lighting, welding, and semiconductor processing. The flow of electric current can generate heat. This is because electrons collide with atoms as they move through the conductor, transferring energy to the atoms. The amount of heat generated is proportional to the square of the current and the resistance of the conductor. This is known as Joule heating. Joule heating is used in electric heaters and incandescent light bulbs. However, it can also be a source of energy loss in electrical circuits. To minimize Joule heating, it is important to use conductors with low resistance and to keep the current as low as possible. Superconductors are materials that have zero resistance to the flow of electric current below a certain critical temperature. When a current flows through a superconductor, there is no Joule heating. Superconductors are used in a variety of applications such as magnetic resonance imaging machines, particle accelerators, and high-speed digital circuits. The development of high-temperature superconductors, which can operate at temperatures above the boiling point of liquid nitrogen, has opened up new possibilities for the use of superconductors in a wider range of applications. In addition to carrying current, conductors can also carry electromagnetic waves. This is the principle behind antennas and transmission lines. Antennas are used to radiate and receive electromagnetic waves. Transmission lines are used to transmit electromagnetic waves from one point to another. The design of antennas and transmission lines is complex and depends on the frequency of the electromagnetic waves. At high frequencies, the skin effect can significantly affect the performance of antennas and transmission lines. Waveguides are hollow conductors that are used to transmit electromagnetic waves at microwave frequencies. Waveguides are typically made of metal and have a rectangular or circular cross-section. The electromagnetic waves propagate through the waveguide by bouncing off the walls of the waveguide. Waveguides are used in radar systems, microwave ovens, and satellite communication systems. Optical fibers are used to transmit light signals over long distances. Optical fibers are made of glass or plastic and have a very small diameter. The light signals are transmitted through the optical fiber by total internal reflection. Optical fibers are used in telecommunications, data networks, and medical imaging. The selection of the appropriate type of conductor for a specific application depends on a variety of factors, including the required current carrying capacity, the operating voltage, the frequency of the signal, the ambient temperature, and the installation environment. It is important to consult relevant standards and regulations to ensure that conductors are installed safely and in accordance with best practices. Always consult with a qualified electrician or electrical engineer for specific applications.